Okay, time to practice assigning oxidation numbers. I'm going to walk you through a bunch of examples here. I'm going to go pretty quick because you can always pause the video and go back. So if we look at our first example here, the first thing you got to do is put on your Captain Ionic hat. That's the most important thing because once we know these are ions, then we can assign the oxidation numbers. And aluminum always makes a +3 ion, and sulfur makes the sulfide -2 ion. So since they're ions, those are the oxidation numbers. And in all of these examples, I'm going to put the oxidation numbers above the elements, and then if we need to keep track of a total, we can put that down below. In general, you're not required to show work on this, but that's a good way to keep track if you want to do it that way. So 2 aluminums at +3. Remember, this means each atom is +3. There's a +6 for the aluminum, and 3 sulfurs at -2 is -6. And of course, the total here has to total to 0 because it's a neutral compound. And remember, there's nothing special about that rule that compounds must total to 0. It's because every time an electron is transferred, one atom loses a charge and one gains a charge, and they cancel out. All right, our second example here is zinc. That's super easy. Elements are 0 because they're bonded only to themselves, so there's no tendency to gain or lose electrons. All right, next example, P2O5. For this one, we're going to put on our molecular hat because these are not ions. And we do have to make an assumption here. Our assumption, remember, is that oxygen is almost always -2. It's only not that when it's bonded to itself or fluorine. And the only common example that you will see of that is O2 itself. So without drawing the dot structure here or checking up, you should assume that oxygen is not bonded to itself in these kinds of structures. And that means we're going to give oxygen a -2. Right? So there are 5 oxygens, so the total there is -10. Which means we need a total of +10 from phosphorus to make it neutral. And because there are 2 phosphorus, each phosphorus is going to be +5. All right. Next example is a polyatomic ion. Now remember, this has a 2- charge, which means 2 electrons have been gained from something else. We don't know what, but it means the total oxidation number will have to be -2 to account for those electrons. And once again, in a structure with oxygen, it's going to be covalently bonded to sulfur. We're going to assume oxygen's not bonded to itself. And again, I'm not asking you dot structures to check that, but it means we'll assume all of the oxygens are -2. Okay? And that means there's -12 from the oxygen here. Now, remember, this time we're after a total of -2. So it shows us that we're missing +10 from the 4 sulfurs. And this is actually an interesting case here. For your level, you're just going to take an average oxidation number. So you need 10 positive oxidation numbers from 4 sulfurs. That's an average of +2.5. Okay, what that really means is if you looked at the dot structure, some of the sulfurs would be +2 and some of them would be +3. But we're not going to worry about that. An average is good enough for us. All right. So those are the first 3 examples. Let's go to the next page. All right, next example, NH420. So this one you should have your Captain Ionic hat on because these are ions, which means this is an oxide ion, which is -2. So we can put that in right away. And this is an ammonium ion. So there's kind of 2 ways to do this problem. We can separate into ions or do it as a whole compound. So I'll do it both ways. Let me do it as a whole compound first. So we've got oxygen with -2. Hydrogen, we've been taught, should be a +1. Okay? And there's 4 hydrogens here, but 2 of the ions, so it's doubled, so that's a total of +8. And this being a neutral compound, we see what we're missing is -6. So -2 and -6 is -8 and +8. So the nitrogen has to give us -6, but remember there's 2 of them over here. So each nitrogen will be a -3. So that's how to do it as a whole compound. If you want to break into ions, we already did the oxide ion by itself, but ammonium is itself an ion, NH4+. And now there's only 1 of them, so it might make it a little bit easier to keep track of the numbers. And hydrogen, again, when bonded with a non-metal is +1, so we have a total of +4 from the hydrogens. Now remember, this ion as a whole has lost an electron, so the total has to equal +1. And we see nitrogen, therefore, must be -3. -3 + 4 gives you +1. So that's the ammonium ion separate, and we really already considered the oxide ion separate. All right. Next example, this is another Kapton ionic. And again, you need to recognize the ions. This is a potassium ion, which is +1 in the first column. And this is a sulfite ion. So we'll do this one both ways. The whole compound has to be neutral. And again, we're going to assume oxygen is always -2. So now we have +2 from the 2 potassiums. We have -6 from 3 oxygens. And what's missing for sulfur? This has to be neutral, so we get, +4 down here, and there's only one sulfur, so sulfur's +4. Okay, so that's how you do it as a whole compound. If you want to do separate ions, we already did the potassium ion as +1, so the sulfite ion is SO3 2-. And again, we assume oxygen is going to be -2 in the ion, which gives us -6 total for the ion. And we have to get a total of -2 for the charge on the ion for the 2 electrons it gained. So again, sulfur has to be +4. So either way, we'll get the same thing for each element, +4 for the sulfur there. Oops, I never put the -3 on nitrogen here. All right, so we got one more page of examples. Okay, first one, super easy. It's elemental, so it's a 0. And again, anything bonded to itself has no tendency to gain or lose electrons. Next one's important because we should recognize this as an acid. And remember, because acids turn into ions in solution, you can almost think of them as ionic. It's pretty much the same thing. So if you think about hydrogen always being +1, or hydrogen or an acid being +1, or as a hydrogen ion, given off by the acid, we're definitely going to get a +1 for hydrogen, which gives us +2 total for the 2 hydrogens. And of course, we assume oxygen is not bonded to itself in this polyatomic ion, so we assume oxygen is a -2, which is a total of -14. Okay? And the whole thing has to be neutral, so we're missing +12 here for the chromiums. And note there are 2 chromiums, so 2 chromiums have to give us this total +12, so each chromium is +6. Right? So that's how to treat it as a compound. If you wanted to break into ions, again, as an acid, hydrogen would just be a +1 ion, but we can do Cr2O7 as an ion as well. Dichromate is a 2- ion. So again, the total now has to come out to -2. Oxygen, we're going to assume, is the -2, and that's a -14 there. And again, we see we're missing +12 for the 2 chromiums to get a total of -2, and each chromium is +6. So same results either way, whether we treat it as a whole compound or as dichromate being a polyatomic ion. Oops, and we're missing a little room on the last one. PF3. So this is back to our molecular hat. And this one's interesting because there's no oxygen or hydrogen, but we just remember our lessons about electronegativity. And if we imagine the structure here, it's going to be phosphorus, okay, attached to 3 different fluorines. You don't actually have to draw out the dot structure. You should know that fluorine does not double bond. So each fluorine has 7 valence electrons and is going to gain 1 electron. So fluorine is going to be -1. Remember, fluorine takes electrons from everything. So each one of them will get that 8th valence electron. And of course, there's 3 fluorines, so that's a total of -3. And that means we need +3 from the phosphorus, and there is only 1 phosphorus. So this phosphorus has to be +3. Okay, that's it. Exciting oxidation numbers isn't too hard. You've got that big practice sheet. I hope you do as many of them as you need to get good at this. If you're good at this, it makes redox super easy. Have a good one.